You've got a 300-page internal policy document, you uploaded it to an AI tool, you ask a very super specific question about it, and the AI just gets it wrong or altogether makes something up. It sounds familiar, right? So, this is the thing that drives people crazy about AI, and it comes down to one fundamental problem. The model was trained on the internet and not on your stuff. So, today we are going to fix that. We're going to talk about RAG, how it actually works step by step, and why it's become the default way that AI systems use your own documents. So, what is RAG and why is it called that? Let's break down the name first because it actually tells you exactly how it works. RAG stands for Retrieval-Augmented Generation. It sounds a little academic, but the idea is really simple. Think of it like an open book exam. The AI is the student, your documents are the textbook. Before the AI answers your question, it flips through the textbook, finds the most relevant pages, reads them, and then answers with the specific information in front of it. That's it. So that is the core idea. The AI isn't memorizing your documents or something. It's looking things up fresh every single time you ask a question. This is the mental model you want to hold on to. That is, it's a cheat sheet the AI writes for itself just for your particular question. Now, how does that actually happen technically? There are two distinct phases here, and most explanations skip over this, so let's be precise here. There are two completely separate phases in a RAG, and it's important you understand both. The first phase is indexing, and this happens before any user even asks a question. You take all your documents like PDFs, Word files, wikis, whatever, and you process them into a searchable knowledge base. This is like a one time setup step, and the second step is more like a runtime. This is what happens live when someone actually asks a question. The system searches that knowledge base, finds the most relevant bits, and hands them to the AI alongside the question. These two phases are totally separate. The indexing can happen overnight, the retrieval happens in milliseconds. Keep this separation in mind because every step we are about to walk through belongs to one of these two phases. So let's start with phase one. Before you can search your documents, you have to break them up. And this step is called chunking, and it is one of the most underestimated decisions in the entire system. Here's the first real engineering problem. You can't just dump a 300-page document into the AI and say, search this, right? AI models have a context window, that is, a cap on how much text they can read at once. So instead, you break your document into chunks. Think of it like cutting a textbook into individual index cards. Each chunk is typically around 300 to 500 words. That is, they're short enough to search precisely, long enough to carry meaning. But here's where it gets a little tricky. If you cut a sentence in the middle, you lose context. If your chunks are too short, they are too narrow, too long, and the retrieval gets noisy. The size and strategy of your chunks directly affects how good your answers will be. Most teams set this once and forget it, but it's actually a tuning knob you should keep coming back to. Okay, so you've got your chunks. Now you need to make them searchable, and this is where it gets genuinely cool. We need to turn text into numbers. This is the part that I find genuinely fascinating. That is to search documents by meaning and not just keywords. You need to convert text into numbers, and not just any numbers. You need numbers that capture semantic relationships. This is what embeddings do. An embedding model like open source models like BGE takes a piece of text and converts it into a long list of numbers called a vector. And here's the magical part. Text that means similar things get similar numbers. So the phrase the dog ran away and the phrase the puppy escaped end up as vectors that are mathematically close to each other in space. The stock market crash lands somewhere completely different. When you embed all your document chunks, you're essentially placing them as points in a multidimensional map where similar content clusters together. That map is what makes semantic search possible. And now you need somewhere to store all those vectors, right? That's where vector databases come in. And no, regular SQL databases won't cut it here. You've got thousands, maybe millions of these vectors now. You need to store them somewhere that lets you search them in milliseconds. That's what a vector database does. Tools like Pinecone, VV8 Chroma, or even PG Vector inside Postgres are built specifically for this. They don't search by filtering rows like a regular database. They use a technique called approximate nearest neighbor search, ANN, to find vectors that are geometrically closest to your query vector, which is obviously incredibly fast. What this means practically is that when you search for what's the refund policy, the vector database isn't doing a keyword matching. It's finding chunks that are semantically similar to that concept, even if the document says returns and exchanges instead. That's fundamentally different kind of search, and it's why RAG can find things that traditional searches actually miss. Okay, okay, we've built our knowledge base. Now we are at runtime. A user types a question. So what happens next? The user types a question. That question immediately gets embedded, turned into a vector using the exact same embedding model you used for indexing. Then that query vector gets sent to the vector database, which runs a nearest neighbor search and returns the top case similar chunks. Usually top 3, top 5, top 10. You configure this. So each chunk comes back with a similarity score. Let's say we have 0.94. It means it is very relevant. 0.51 means loosely related. Some systems add a re-ranking step here using a second, more precise model to reorder those chunks before passing them along. And this whole retrieval step typically happens in under 100 milliseconds, and the user doesn't even notice it, but it determines everything about the quality of the final answer. Okay, so now you've got your retrieve chunks, and here comes a step that ties everything together. This is where you actually talk to the LLM. Now we take the retrieve chunks and we literally paste them into the prompt. The prompt the LLM receives looks something like this. You are a helpful assistant. Use only the following context to answer the user's question. Then you paste in chunk 1, chunk 2, chunk 3. Then you paste in the user's question. That's it. There's no magic API call. You're just concatenating text and handing it to the model. And because the relevant information is right there in the prompt, the model can answer specifically and accurately instead of hallucinating from its general training. And this step is called Retrieval-Augmented Generation because you're augmenting the generation step with retrieve context. You have taken a general purpose AI and given it temporarily the exact knowledge it needs to answer your specific question. Now, and this is the part most tutorials skip, RAG is not magic. There are real ways it fails, and you should know about them before you start building anything. Let's be honest about where this breaks. Failure mode 1 is bad chunking. That is, if you slice your documents poorly, splitting ideas across chunks, making them too short or making them too long, Retrieval never finds the right thing. Garbage in and garbage out. Failure mode 2, that is, Retrieval misses. Semantic search is powerful, but it's not exactly perfect. So if the user's question uses very different vocabulary than your documents, the vector might not match. Keyword search sometimes outperforms embeddings here. Failure mode 3, context overflow. You retrieve 10 chunks, they're all somewhat relevant, but you've stuffed 8,000 tokens into the prompt, and now the model loses track of what it is actually doing. Smaller and more precise beats bigger and noisier. And failure mode 4, the model ignores the context anyway. Yes, this happens. LLMs can drift towards their training data instead of the provided context, especially if the context contradicts common knowledge. And your prompt needs to explicitly and firmly instruct the model to use only the provided context. So people hit these failure modes and they start looking for better approaches. And there are genuinely clever ones. Let me show you three techniques that actually move the needle. Technique 1, that is hybrid search. Instead of using only semantic vector search, you run keyword search like BM25 in parallel and merge the results. This catches exact matches that embeddings miss and catches conceptual matches that keywords miss. So it is like best of both worlds. Then you have technique 2, which is re-ranking. Your vector search returns the top 20 candidates quickly, but approximately, obviously. And you then run a more precise cross encoder model, which is a bit slower but more accurate, to actually rescore and reorder those 20. So you end up with better top 3 results. And technique 3 is one of my favorite, which is HyDE, which stands for hypothetical document embeddings. That is, instead of embedding the user's question directly, you first ask an LLM to generate a hypothetical answer, even though if it's not accurate. Then you use that particular, hypothetical answer as the search query. It turns out that a hypothetical answer is semantically closer to a real document chunks than the short question is. It is a bit weird, but it works really well. Also, there is this one question that comes up every time I talk about RAG. That is, why not just fine tune the model instead? Honestly, it's a great question, and the answer is more nuanced than most people expect. Fine tuning means retraining the model's weights on your specific data. RAG means giving the model your data at inference time without touching the weights. So, which do you use? Here's the clearest way I can put it. If your data changes frequently, that is new documents, updated policies, live databases, you got to use RAG because you can't retrain a model every time your document changes, right? If your data is relatively static and you're trying to change how the model reasons or writes, like its style, tone, domain expertise, then fine tuning starts making sense. And here's the thing most people miss, that these aren't mutually exclusive. The most powerful production systems do use both. They fine tune a base model for domain reasoning and communication style, and then they plug RAG on top for up to date specific citable knowledge. So RAG is cheap, fast, and updatable. Fine tuning is expensive, slow, and static. Know which problem you actually have before you choose. Alright, let's put all of this together. Here's the full picture and where I would actually start if I were building this from scratch today. Here's the full stack. You chunk your documents, you embed them with a model, you store those embeddings in a vector database. At query time, you embed the question, retrieve the top chunks, stuff them into a prompt, and hand that to an LLM. That's RAG, that's the whole thing. If I was starting today, I would start with LangChain or Llama Index to wire the components together, Chroma or PG Vector for the vector store, and OpenAI's text embedding 3 small for embeddings. So that's a working RAG system you can have running in an afternoon. So that's about it for this video. Like and subscribe if you find this video useful. I'll see you in the next one. Thank you.